In this section, we're going to minimize linear programming problems with mixed problem constraints using the Big M method. Remember, the only condition for using the Big M method is that the right side of each problem constraint has to have a non-negative number. Because we have mixed constraints, we have to deal with each constraint differently. In a less than or equal constraint, we're going to add a slack variable. In a greater than or equal constraint, we must subtract a surplus variable to gain equality. But if we only subtract a surplus, this is going to lead us to a non-feasible solution, as we're going to see. So to counter this, we add an artificial variable to the constraint as well. The artificial variable has no meaning in the original problem. Its sole purpose is to help us find a basic feasible solution so that we can apply the simplex method. To ensure that the artificial variable does not become a part of the optimal solution to the original problem, we introduce a very large penalty to the objective. So we create this penalty by choosing a positive constant m so large that the artificial variable is forced to be 0 in any final optimal solution of the original problem. Then we add the term negative m times the artificial variable to the objective function for every artificial variable that's been introduced. We use the same m for each one. And since m can be as large as we like, when using a computer program, it's often chosen to be the largest number that a computer can hold. To form the modified problem, we first make sure that all problem constraints have non-negative constants on the right side. If there's a negative constant, we multiply both sides by -1, and if it's an inequality, that's going to reverse the direction of the inequality. If we have a less than or equal constraint, we're going to add a slack variable. In each greater than or equal constraint, we're going to subtract a surplus variable and add an artificial. In any equal constraints, we're going to add an artificial variable. And then we subtract m times the artificial variable for every artificial variable that we've added to the objective. To solve using the Big M method, we form the preliminary simplex tableau for the modified problem. We use row operations to eliminate the m's in the bottom row of the columns corresponding to the artificial variables. That gives us the initial simplex tableau. Then we use the simplex method to solve. We can relate the optimal solution of the modified problem to the original problem. If the modified problem has no optimal solution, neither does the original problem. If all artificial variables are 0 in the optimal solution to the modified problem, then we can delete those variables to find an optimal solution to the original problem. However, if any artificial variables are non-zero in the optimal solution to the modified problem, that means the original problem has no optimal solution. So this table gives a summary of the different problem types and simplex solution methods. Now notice in number 2, we have minimization with only greater than or equal problem constraints. The right side constants can be any real numbers, but the coefficients are non-negative. And to do that problem, we form the dual problem and solve using the simplex method. However, if you're minimizing with mixed problem constraints, the right side constants have to be non-negative, but the coefficients of the objective can be any real number. And these we are going to solve by maximizing the negative of the objective function and use the Big M method. So to minimize an objective function using the Big M method, we need only maximize its negative. So in the first example, we're going to minimize c equals 10x1 plus 16x2 minus 5x3, subject to the constraints x1 plus 3x2 less than or equal to 7, 4x2 plus x3 less than or equal to 5, and x1, x2, and x3 non-negative. So note, this can't be worked using the dual method. Even though the constraints have less than or equal, we could change those to greater than or equal. The problem is that there's a negative number in the objective function. So that's why we have to use a different method. So because the constraints are both less than or equal, I just have to add a slack variable. So I don't have to add any artificial variables to this problem at all. What I do need to know is that to minimize the objective, I'm going to maximize its negative. So to do this, we're going to introduce a maximization objective function t. So min c is equal to negative max t. So since c is 10x1 plus 16x2 minus 5x3, that gives us t equals negative 10x1 minus 16x2 plus 5x3. So we've just changed all the signs to create a new objective function called t, and we're going to find the max of t. We're going to form the modified problem by adding slack variables to the constraints. So we have x1 plus 3x2 plus s1 equals 7. 4x2 plus x3 plus s2 equals 5. And x1, x2, x3, s1, and s2 are non-negative. So now we have to get the objective ready to go into the tableau. So we're going to get it equal to 0, keeping t positive. So we move everything to the left to get 10x1 plus 16x2 minus 5x3 plus t equals 0. So putting this in a tableau, we have column labels x1, x2, x3, s1, s2, and t, and then we have our constant column since this is an augmented matrix. Row 1 is 1, 3, 0, 1, 0, 0, 7. Row 2 is 0, 4, 1, 0, 1, 0, 5. And the last row is 10, 16, negative 5, 0, 0, 1, 0. Now, we didn't introduce any artificial variables, so we don't have any m's in the bottom row. So we're just going to use the simplex method. Note that the basic variables are s1, s2, and t. And the most negative number in the bottom row to the left of the objective column is negative 5, and that's in column 3. So x3 is going to be the entering variable. Now, in that pivot column, we have a 0 and a 1. So the 0 in row 1 automatically disqualifies it as a pivot row. So row 2 is our pivot row. The pivot element is already a 1, so I just need to get zeros in the rest of the column. So I already have a 0 in the position that I need in column 1 in row 1. So I just need to change the negative 5. So I multiply row 2 by 5, add it to R3 to get a new R3. So the new row 3 is 10, 36, 0, 0, 5, 1, 25. Now this tableau is optimal. There are no negative numbers in the bottom row to the left of the t column. S1, x3, and t are my basic variables. So S1 has value 7, x3 has value 5, and t has value 25. Now remember, min c equals negative max t. So since t has value 25, min c has value negative 25. So the solution to the minimization problem is that the minimum value of c is negative 25 when x1 is 0, x2 is 0, and x3 is 5. For this example, we're going to minimize p equals 2x1 minus 10x2 subject to the constraints x1 plus x2 less than or equal to 20, 5x1 plus 3x2 greater than or equal to 75, and x1 and x2 greater than or equal to 0. So in order to minimize p with mixed problem constraints, what we're actually going to do is we're going to create a maximization function, and we're going to take the negative of it. So min p is equal to negative max t. So to create t, we just change all the signs of our original objective. So we're going to maximize t equals negative 2x1 plus 10x2. So we're going to use that along with the constraints to form the modified problem. So the first constraint is a less than or equal, so we add a slack variable. So this becomes x1 plus x2 plus s1 equals 20. The second constraint is greater than or equal, so we subtract a surplus and add an artificial. So this becomes 5x1 plus 3x2 minus s2 plus a1 equals 75. Now, because I added an artificial, I must subtract m times the artificial from the objective. So my new objective function is t equals negative 2x1 plus 10x2 minus ma1. And all of my x's, all of my s's, and all of my artificial variables are non-negative. To get ready to go into the matrix, I got to rearrange the objective function. So I want it to be equal to 0, and I want t to stay positive. So I'm going to move everything to the left. So I have 2x1 minus 10x2 plus ma1 plus t equals 0. So now let's form the preliminary tableau. So my column labels are x1, x2, s1, s2, a1, t, and then I have my constant column since this is an augmented matrix. Row 1's values are 1, 1, 1, 0, 0, 0, 20. Row 2's values are 5, 3, 0, negative 1, 1, 0, 75. And row 3's values are 2, negative 10, 0, 0, m, 1, 0. Now, right now, S1, S2, and T are the basic variables, but the problem is that S1 equals 20 and S2 equals negative 75. But remember, S2 has to be non-negative, so that's why we introduce the artificial variables. So to solve this, we first have to get rid of the m in the A1 column to form the initial tableau. So we're going to multiply row 2 by negative m and add it to row 3. So that gives us a new row 3 of negative 5m plus 2, negative 3m minus 10, 0, m, 0, 1, negative 75m. So now I can see that my basic variables for this tableau are S1, which is 20, A1, which is 75, and T, which is negative 75m. And this is my initial tableau. So now I'm ready to begin the simplex method by choosing the most negative value in the bottom row to the left of the objective column. So that's going to be negative 5m plus 2. So x1 is the entering variable. Because everything in the pivot column above the last row is positive, I compare the quotients to choose the pivot row. So 20 over 1 is 20, 75 over 5 is 15, so I know that row 2 is the pivot row. Right now, as the pivot element, I have the number 5. I need to change the 5 to a 1. So I'm going to multiply that row by 1/5. So that's going to give me a new row 2 with values 1, 3/5, 0, -1/5, 1/5, 0, 15. Now, I need zeros in every other place in the pivot column. So I'm going to use -R2 plus R1 to get a new row 1. So those values will be 0, 2/5, 1, 1/5, -1/5, 0, and 5. Now, to get a 0 in the column 1 bottom row, I have -5m plus 2. I'm going to have to add 5m and subtract 2. So I multiply row 2 by 5m minus 2. So that'll cancel out -5m plus 2. And you can see the computations for the rest of the row below there. But I end up with values 0, -56/5, 0, 2/5, m minus 2/5, 1, and -30. So the basic variables for this tableau are S1, X1, and T. So this is not optimal because I do have a negative number in the bottom row to the left of the objective column, and that's -56/5. So that tells me that column 2 is the pivot column, so X2 is the entering variable. Now, because everything above the bottom row is positive, I'm going to have to compare the quotients to figure out which row to pivot. So I divide 5 by 2/5. So that's the same thing as saying 5 times 5/2. So that gives me 25/2, or 12.5. 15 divided by 3/5 is the same thing as multiplying 15 by 5/3, and that gives me 25. So row 2 is 25. Row 1 has a quotient of 12.5, so row 1 is the pivot row. As the pivot element right now, I have a 2/5. I need to make that a 1. So I'm going to multiply row 1 by 5/2. So that gives me 0, 1, 5/2, 1/2, -1/2, 0, 25/2. Now I need to get zeros in the rest of the pivot column. So to do that, I'm going to use the operation -3/5 R1 plus R2 to get a new row 2. And those values are 1, 0, -3/2, -1/2, 1/2, 0, 15/2. To cancel the -56/5, I'm going to multiply row 1 by 56/5 and add it to row 3. So that gives me 0, 0, 28, 6, m minus 6, 1, and 110. And you can see the computations for row 2 and row 3 worked out below. So for this tableau, X2, X1, and T are the basic variables, and we can see that this is optimal because I cannot choose a pivot column. So let's get the solution to the modified problem. So here, the value of T, max T, is 110. Remember that min C equals negative max T. So because max T is 110, min C is negative 110. So the optimal solution is min C equals negative 110 when x1 equals 7.5 and x2 equals 12.5. Now remember, The reason that we know this has an optimal solution is because the artificial variable has value 0. If the artificial variable had a non-zero value, this would have no optimal solution. So let's look at an application problem. A person on a special diet requires at least 120 units of protein and at most 32 units of carbohydrates daily. The diet will consist entirely of 3 liquid diet foods, A, B, and C, whose contents and costs are given in the table. How many bottles of each brand of diet food should be consumed daily in order to meet the protein and carbohydrate requirements at minimal cost, and what is the minimal cost? So we can see that in our table we're given the units per bottle for A, B, and C, for the protein, the carbohydrates, and the cost per bottle in dollars. So let's set up our problem. So first, let's define our variables. So we want to know how many bottles of each brand of diet food should be consumed daily to minimize the cost. So we're going to let x1 be bottles of A, x2 be bottles of B, and x3 be bottles of C. So our objective function that we're trying to minimize is going to be C equals 0.46 x1 plus 0.27 x2 plus 0.7 x3. We're told that the special diet requires at least 120 units of protein. So let's look at the protein content of each type. So we have 10 for A, 10 for B, and 20 for C. So that gives us the 10x1 plus 10x2 plus 20x3 greater than or equal to 120 as the protein constraint. We're told that the person can have at most 32 units of carbohydrates daily, so we're going to need a carb constraint as well. So that's going to be 2x1 plus 3x2 plus 4x3 less than or equal to 32. x1 and x2 and x3 will be non-negative because they cannot consume a negative number of bottles. Now, because we're minimizing with mixed problem constraints, what we're actually going to do is maximize the negative. So we're going to use t equals negative 0.46 x1 minus 0.27 x2 minus 0.7 x3, and we're going to maximize that function using the protein and carbohydrate constraints. Let's form the modified problem. The first constraint is greater than or equal to 120. So we're going to subtract a surplus and add an artificial variable. So we have 10x1 plus 10x2 plus 20x3 minus s1 plus a1 equals 120. The second constraint, the carb constraint, was less than or equal to 32. So to gain equality, we add a slack variable. So this becomes 2x1 plus 3x2 plus 4x3 plus s2 equals 32. Now, because I added an artificial variable to the first constraint, I've got to subtract m times a1 from the objective. Now, x1, x2, x3, s1, s2, and a1 are all non-negative, and so we're ready to get the objective function ready to go into the matrix. So we move everything to the left so that we can get a 0 on the right. So we have 0.46 x1 plus 0.27 x2 plus 0.7 x3 plus ma1 plus t equals 0. So from this we can form the preliminary tableau. So my column labels are the x's in order, x1, x2, x3, the s's, s1 and s2, the artificial variable a1, the objective t, and the constant column. So row 1 is 10, 10, 20, negative 1, 0, 1, 0, 1, 20. Row 2 is 2, 3, 4, 0, 1, 0, 0, 32. And row 3 is 0.46, 0.27, 0.7, 0, 0, M1, 0. Now, the basic variables for the preliminary tableau are S1, S2, and T. But the problem is that S1 is negative 120, and S1 has to be non-negative. So that's why the artificial variables are introduced, and to account for this, the first thing we do is get rid of M in the A1 column to form the initial tableau. So to get rid of the M in that column, I'm going to have to multiply row 1 by negative M and add it to row 3. So that gives me a new row 3 of negative 10M plus 0.46, negative 10M plus 0.27, negative 20M plus 0.7, M 001, negative 120M. So this is the initial tableau. Note that the basic variables are now A1 representing row 1, S2 representing row 2, and T representing row 3. So let's perform the simplex method. So we choose the most negative number in the bottom row to the left of the objective column. In this case, that's negative 20M plus 0.7. So the pivot column is column 3, which makes x3 the entering variable. Now, in that pivot column, both the 20 and the 4 are positive, so we're going to compare the quotient to decide which would be our pivot row. So 120 over 20 is 6, 32 over 4 is 8, so that means that row 1 is the pivot row. So right now the pivot element is a 20. I need a 1, so I'm going to have to multiply row 1 by 1 over 20. So that gives me values 0.5, 0.5, 1, negative 0.05, 0, 0.05, 0, 6. Now that I have a 1 in the pivot element position, I need zeros in the rest of the column. So I'll use the commands negative 4 R1 plus R2 to get a new row 2, whose values will be 0, 1, 0, 0.2, 1, negative 0.2, 0, and 8. And for row 3, I'm going to use the command 20M minus 0.7. I'm going to multiply that by R1 and add it to row 3. And that's going to give me 0.11, negative 0.08, 0, 0.035, 0, M minus 0.035, 1, and negative 4.2. And you can see the computations for both row 2 and row 3 here. The basic variables for this tableau are x3, s2, and t. But this tableau is not optimal. I see that I have negative 0.08 in column 2, which makes column 2 the pivot column. So x2 is going to enter the basis. Now, 0.5 and 1 are both positive, so let's compare our quotients. So 6 divided by 0.5 is 12. 8 divided by 1 is 8. So because 8 is smaller, row 2 is the pivot row. So S2 is the exiting variable. Note that I already have a 1 in the pivot element position, so I just need to get zeros above and below. So I'll use the command negative 0.5 R2 plus R1 to get a new row 1, whose values will be 0.5, 0, 1, negative 0.15, negative 0.5, 0.15, 0, 2. Row 2 remains the same at 0, 1, 0, 0.2, 1, negative 0.2, 0, 8. And row 3, I use the command 0.08 times row 2 plus row 3. So that gives me values 0.11, 0, 0, 0.051, 0.08, m minus 0.051, 1, and negative 3.56. And you can see the computations for row 1 and row 3 below. So this tableau is optimal. There are no negative values in the bottom row to the left of the objective column. And I see that the basic variables are x3 representing row 1, x2 representing row 2, and t representing row 3. Now notice that the artificial variable is 0, so that means that this is going to be a feasible solution here. So I have that x1 is 0, x2 is 8, and x3 is 2. Now, the max t value is negative 3.56. But remember, the original problem is to minimize c. So min c is equal to negative max t. So since max t is negative 3.56, min c is 3.56. So our solution to meet the protein and carbohydrate requirements at minimal cost is 8 bottles of B, 2 bottles of C, and 0 bottles of A to be consumed daily. The minimum cost per day is $3.56.